Hello class, this is another mini lecture. I got a question about concerning the Nernst and Goldman equation. So I thought that I would take a little bit of time and go over these. This is most of the pertinent information here is coming straight from the textbook from pages 41 to 43. In the sections forces that create membrane potentials, which goes over the Nernst equation. And then the next section, electrochemical equilibrium in an environment with more than one permeant ion, where you can find the Goldman equation information. And I'll do just a little bit of extra background here in hopes that it sort of adds to the conceptual idea behind these equations. And so starting with the more simple one, the Nernst equation, which we saw before, and talked about in class before, as giving us, allows us to calculate the equilibrium potential, which is Ex. X, of course, being a particular ion that we're interested in, the ion that's permeable to the membrane. And so this allows us to calculate, based on the concentrations of the two sides of the membrane of the ion, what the resulting equilibrium potential will be. So when they reach that electrostatic and chemical equilibrium, what will be the difference in charge across that membrane, or the potential? As we went over in class, this top equation here is listed in the book, and so is the bottom equation. These equations are equal to each other. And if you're looking up equations online or trying to get answers online, you might run into a little bit of confusion because there are different versions of this equation. The more simple one is the one below that uses the log base 10, which is represented by log. And that's just easier to work with, I think, conceptually, than the natural log. Both are like the inverse exponent function. And so it's doing the opposite of a exponent. But I'll talk about that in a little bit. First, I want to focus on the this right here, and how we get this number 58 from this. And so as I described in class, these different letters here in the circle are different constants, or most of them are. Or actually are. Well, let's see. The R is a constant. It's the gas law. This is a constant. And temperature T is not a constant, but it varies depending on what you're working with here, often at room temperature. F is the Faraday constant, and which is a measurement of electrical charge within of a certain number of it's like a really large number of electrons. And then Z will change with the ion. This is the charge of the ion. So let me show you mathematically how we get from what's in the circle here to our 58. So here's our original equation here. And if we were to write all this out, I'm just going to work on this section right here, right now. And so the gas constant is 8.314, and the units for that are joules, which is a measurement of energy, per moles Kelvin. So it's the amount of energy in a certain amount of something at a certain temperature, or per density temperature. Or not even density, just amount of something. And of course our temperature This is, for this equation, is the absolute temperature, so we're using the Kelvin scale. And so if I were to use, for example, let's see, since we want to get to our 58, which expresses this equation at room temperature, let's make sure we get the correct Kelvin for room temperature. Now, in most scientific studies, what's considered like the standard room temperature, when you see like room temperature, they're talking about 68 degrees Fahrenheit. So 68 degrees Fahrenheit is 293 degrees Kelvin. And let's say we're working with potassium here, which is a go-to example. So Z for potassium will be +1. And we're going to multiply this by the Faraday constant, which is a quite large number. 96,000. 485.3. And the units for the Faraday constant is coulombs per mole. Coulomb is a measurement of charge, and coulombs equals joules per volt. So for those of you who are interested in knowing like how all of these units kind of cancel out, because eventually that constant, that 58, its units are millivolts. And so coulombs equals, I'll just write a little note here, coulombs equals joules per volt. So if you go through here, you'll see that everything cancels. The Kelvin in the numerator cancels with Kelvin here in the denominator, or moles, and you can go through and do remember your sort of how your signs switch, right? So moles in the technically the denominator here, and that's in the denominator of the denominator, which makes it the numerator. So those moles cancel out. The coulombs are joules per volt, so that actually the joules cancel out with that joules. You're left with the voltage. And so the answer we get here its units will be voltage. And then we can reduce that to millivolts, because it will be quite a small number. Okay, and so let's figure out what that number is real quick. So you can grab your calculator, and I've got mine here ready to go. So we have the gas constant, 8.314 multiplied by 293. And so I'm going to reduce it here. 2,436 divide by the Faraday constant, right? 96,485.3. What does that give us? All right. Doing the math here real quick on my calculator. 485.3. All right, so that gives us 0.0252. Now remember, this is expressed in volts. If we want to convert this to millivolts, we would multiply this by 1,000, because there are 1,000 millivolts in 1 volt. And so this gives us 25.28. I'm rounding. Now this is not our 58, which apparently is what it's supposed to reduce to. But that's because, if you remember, over here, 58 is associated with this different version of the equation that uses log base 10 instead of natural log. So in order to convert that, it's a pretty easy transformation to convert that natural log to log base 10. And the way you do that is you multiply it by 2.3026. All right, since we're converting. If that sort of reduced equation was still using natural log, the constant would be, and we would have learned in class, was 25.28. But let's multiply this by our conversion from natural log to log, 2.3026. And we have 58.13. So there it is. There is our constant for the new equation. That's where the 58 comes from. You could repeat this, and you could change this to body temperature, which would be 300. Oh, sorry, that's not right. But yeah, that is right. 310 degrees Kelvin that's approximately like 98.5, 99 degrees Fahrenheit. So, and even though mammalian body temperature ranges quite a bit across species, that's close to humans. If you were to redo this equation with 310 instead of 293, you would find that it would equal, after you do all of this, 61 millivolts. And that's what the units are down here, millivolts. Remember, because we converted from volts to millivolts right here by multiplying by 1,000. And then doing this transformation of 0.23 so that we can work with log base 10 now. So that's where the 58 comes from and why we have it. And that's why it's different. That's why it goes up slightly when you're working with body temperature versus room temperature. Because the numbers that go into the equation change the temperature. Okay, let's do a quick example. You may see this on the something similar to this on the exam. And like I said in class, you should know the Nernst equation by heart. So I'm not going to write it on the exam. So you should know this E of x equals 58 over z. Multiplied by the log of concentration of the outside versus concentration of the inside. And let me fix this little bit here. All right, this should be x, not the concentration of N. There we go. So on the exam, I may give you this just concentrations of the inside and outside of a membrane, the extracellular space versus the intracellular space. And I'll tell you the ion potassium, so you'll know that it's +1, so you'll know what value to give to the Z. And I may even say something like, this is in vitro experiment in the laboratory. And so that's a wonderful spelling, isn't it? Or wonderful handwriting. Let me try that again. With thicker. Here we go. Third time's a charm. So I may say that it's an in vitro experiment. So you should be able to know that, like, okay, so this is going to be a room temperature problem. If I said in vivo, then you would know it's inside of the organism. And I would be clear to make sure you knew what organism. So if I said a rat, could safely assume that it's close to body temperature of ours, so that you would switch to 68 instead of 58. But this one in particular is in vitro, so we're working at room temperature. It's 58, so we want to know what the equilibrium potential is. And this is how we fill in the equation. 58, our constant, right? And this is millivolts over the charge of the ion, which is +1. And that's multiplied by the log of, and our concentrations are on the outside, 20 millimolar, and on the inside, 40 millimolar. Okay, so, and if we do that, we find, and I'll just sort of do a little intermediate step here. 58 divided by +1, that's our 58 millivolts. And we're multiplying this by the log of 20 over 400, which reduces to 1 over 20. And so you can do the math on this. The log base 10 of 1 over 20 times 58. And this gives us negative 75.5 millivolts. And this is because it's negative, because if you do 1 divided by 20, which is the same as 20 divided by 400, it's 0.05, and anything below 1, the log of anything less than 1, gives you a negative number. It ends up being, I'll do another intermediary here, 58 times negative 1.3. And that's where the negative number comes from. So that's a simple example. You will be, for sure, we'll see something like this on the exam. Now this is the Goldman equation, but let me, before we go into the Goldman equation, let's do something different here to highlight, and I'll tell you what I'm trying to highlight here. I'm trying to show what is the reason for this difference in the Goldman equation. The Goldman equation should look very similar to the Nernst equation. This was an equation that was developed specifically to calculate the equilibrium potential, or specifically the membrane potential, which is the equilibrium potential of these three ions, of potassium, sodium, and chloride, taking into account their relative permeability, which is highlighted by the P coefficients here. But you'll notice that when it comes to chloride, we've switched the concentrations. In the Nernst equation, the concentration of the outside of the membrane is in the numerator, and the inside, the intracellular space, is on the denominator. But we've switched it in the chloride. Now, why have we switched it? Well, we've switched it because the valence of this ion is negative. Sodium and potassium are positive. But let's take a look of what is it about being negative that necessitates this switch of putting the inside concentration on the top and the outside concentration on the bottom. So let's go back to this example here. And what I'm going to do is we're going to just do an interesting switch here. So let me erase this here. And I'm going to solve this part of the equation by switching the concentrations. And we'll see what happens. So instead of putting the outside on the top like the Nernst equation requires, and I'll do this in red to show that the difference, to show you what I'm doing that's different. is that I'm going to put the inside of the inside concentration on the top, which is what we see in the chloride version of the Goldman equation. So if I put 400 on top and 200 on the bottom, this reduces to 58 millivolts times the log of 20 into 40. 20 into 400 is 20. Remember before it was 1 over 20. What's the log of 20? Well, if you are comfortable with sort of understanding the kind of pattern that comes along with log base 10, you could guess you would know right away based on what we did previously. But you can do your calculator, 20 log, and you find that we have an equation that says 58 millivolts times, it's not negative 1.3 now, but it's positive 1.3. And that's because for log base 10, we find that this is the relationship. Log of A over B equals negative log of B over A. And if I'm not mistaken, I think maybe someone in class actually talked about this relationship. So it's because of this relationship, you can see how A and B are switched when it becomes negative. Log of A over B equals log of B over A when it's negative. And so when the ion is negative, chloride, we switch what's on top and what's on bottom. So this equation takes into account the charge of the ions. Right? So any negative charge, the concentrations need to be switched, which is what Goldman did and recognized. So let's take a look at an example, knowing that this is sort of like kind of putting three Nernst equations together, so to speak, in a way. We're gonna consider all three of these ions, which are the three major players when it comes to determining the membrane potential of a neuron. And we must necessarily take into account what their relative permeabilities are. So you're likely to see something like this on the exam. And I may say, like we're doing in vivo study in rat neurons, for example. And so let's solve the equation for this using the Goldman's equation. And so first, I'm not using 58, but I'm using 61 because we're at body temperature. Millivolts. Multiplied by the log, and I'll do my best to fit everything in here, of the concentrations and permeabilities of potassium, sodium, and chloride, all three. So potassium first, and let's make things a little bit easier on the eyes if I can keep the colors straight here. We'll make potassium red, sodium green, yes, and chloride blue. So remember, all the concentrations here are going to be multiplied by their permeability, relative permeability factors, which are these numbers here. Okay, so you can imagine doing this question on the exam. I'm giving you the chart here of the permeabilities, but you have to come up with the Goldman equation. So going by memory, we know that we need the concentration of potassium, and it's outside over in for our positive ions. So that is 5 over 125. And we need to multiply it by the permeability constant. So 1 times that. And we're going to add it to the next ion, which is sodium. Again, our outside for sodium is 145. And our inside for sodium is 15. And we have to multiply this by its permeability constant, its relative permeability, 0.04. So relative to how much potassium can get through, which is the most permeable because it's gotten the 1, it is not very permeable at all, 0.04. Not much sodium gets through the membrane at rest. It's right here we're calculating our, these are the specific numbers for our neuron at rest. These numbers would be very different if we were calculating the concentrations and permeability during an action potential. And what's left? Chloride. Yes, we want blue. And so remember, chloride is negative. Because of that relationship with log base 10, we're inverting it. So the inside goes on top. So the concentration is 13 for inside, which I'm putting on top, and 150 on the bottom. And its permeability is almost half of what potassium is. 0.4, 0.4. Okay. So, and I'll sort of do things piecemeal here. So we have 5, and I'll try to keep the colors here. 5 plus 5.8, and 0.4 times 150. 0.4 times 13 is 5.3. .25, 0.04 times 15 is quite small, 0.6. And 60. I'm doing my best here to not confuse you with the colors. And 60 for our chloride. And so we add these together. I'm just going to do black now since we're adding everything together. We have 16 over 185.6. And what does this equal? Right, and remember, let's not forget this part, log. Log of 16 over 185.6. That equals negative. You see, it's less than 1, so we know that we should get a negative number. Negative 1.06. Multiplied by, let's not forget, our 61 millivolts here. That gives us negative 64.9 millivolts as our resting membrane potential. Okay. Now, and you can think about this conceptually, like, does this make sense? You can look at the chart at the top, and you can say, okay, the most permeable is potassium. So this is likely going to dictate the most of, it's going to be responsible for the lion's share of the membrane potential. And so you can see that there's a lot of potassium on the inside of the cell versus the outside. So if you make the membrane permeable to potassium, potassium is going to move from inside of the cell to the outside of the cell, moving down its concentration gradient. When it does that, it's taking a positive charge with it, right, from the inside to the outside. So every time a potassium goes to the outside is becoming a little bit more positive, and the inside is becoming a little bit more negative. Now, if you take a look at sodium, we can almost neglect here because its permeability is so small, it's going to have a negligible movement. Chloride is kind of close to half, so you can think about what's going to happen to chloride. There's more chloride on the outside of the cell, so it's going to move down its concentration gradient and go into the cell. And every time chloride moves from the outside to the inside, it's taking a negative charge from the outside to the inside. So the outside becomes a little less negative or more positive, and the inside becomes more negative or less positive. And so potassium and chloride are doing the same thing. Chloride is moving negative charges into the cell because it's moving down its concentration gradient. And potassium is moving positive charge out of the cell. So while potassium is taking plus out of the cell, chloride is moving negative into the cell. So it's no surprise here through the actions of potassium and chloride that it gives us a negative membrane potential because it has both of these ions that are moving in that direction. Right. So conceptually, you should be able to sort of look at a chart like this, and even before you do the Goldman equation, predict with a pretty high degree of accuracy, am I going to end up with a negative membrane potential, or am I going to end up with a positive membrane potential? Now you can look at this chart, and if you switch things up and made potassium and chloride negligibly permeable and gave 1 to sodium, all of a sudden things change. Sodium, more concentrated on the outside of the cell, if it was permeable to the membrane, it would rush into the cell down its concentration gradient, bringing positive charge with it and making the membrane potential positive, which is not the case here because it's not permeable. But that is the case during an action potential. And we'll get into more details of that in subsequent lectures, and you don't have to worry too much about that in terms of studying for the exam. So I hope this clarifies some things about the Nernst and Goldman equations. I hope these examples were useful. I hope it was maybe conceptually useful to take a look at where the 58 comes from, where the 61 comes from those other constants, and how it's part of that constant comes from the transformation from the natural log to the log equations. So feel free to give me an email if you have any other questions or concerns about this or any other materials, and I'll do my best to answer them. We'll have some time on Monday in which I could meet, and I'll be checking my emails regularly. Happy studying. I hope everyone's having a nice weekend. See you soon.